To clarify, it's not that I don't know how to live stream. When there is somebody else, I don't live stream.
Okay. Now we are live. We may have been live for your previous sentence also.
Fine. Okay, let's get started. Yeah, so what we'll do today is the proof of the dense model theorem. Dense model theorem. And this theorem was originally much proved by Green and Tao. That was a slightly more complicated version of the theorem than what we saw last time. And then it was given simplified subsequently by two groups, Reingold, Trevisan, Tulsiani, and Vadan, and independently by Gowers. And both the proofs are more or less similar. What we will do today is see the proof due to RTTV. RTTV's version of DMT and its proof. And I'll state it slightly more generally than what the way it was stated yesterday. This will actually address Jayakumar's question from last time. So let's look at the setting. What's the setting we have? So there is so we were working with Zn and stuff that time. Let's make things more general. We have some set X. And think of X as some finite set for now. This might work for other sets. I haven't checked it. So let's just think of some X as some finite set. And we are looking at real valued functions on this set. But among these real valued functions, so we will be looking at the set of all functions f, which are f going from X to R. This is a set of all real valued functions, it's a vector space. But among them, we'll be considered with a particular class of test functions. Say phi. Phi is some subset of f, and phi contains only of functions of the form x2 minus 1, 1. Actually, let's make it even simpler. Let's call it just 0, 1. It's some set of bounded functions in this class. For instance, last time, one set of functions which we considered in this class, if you recall from last lecture, were the cut functions. Phis corresponding to the cuts, but I'm going to talk about more generally than this. And so we are given something like this. We'll say that f and f prime, two functions in the class, are epsilon indistinguishable with respect to this class phi if for all test functions phi in this class, we have that f minus f prime inner product with phi is at most is epsilon. That is, this test function can't distinguish, whereas here the inner product is the usual notion of inner product. F inner product G is just expected value of f of x, g of x uniformly chosen from the set X. So this is the notion of indistinguishability we'll work with. This is exactly similar to what we had defined last time. Okay. And then we'll call certain things measures. So we'll call, so nu is a function from x to 0 to infinity is a measure if two things are satisfied. One is nu is greater than or equal to 0. That is, I've defined it, I'm just making it more explicit. And 2 is expected value of nu equals 1. And the most natural measure, so what are examples of these measures? Examples of measure is the uniform measure, the all ones function on x. That is, it maps all of x to the number 1. This is measure. Or you can take any particular set S of x, and nu could be, say, the indicator of S, but we'll scale it so that, so how should I scale it so that the expectation turns out to be this object? I'll have to multiply it by mod x, and this one. So the scaling will take care of it. So nu is this is also this one. Notice that nu, unlike the usual uniform measure, which is bounded by 1, this need not be bounded. This because of am I messing this up? Yeah, no, this need not be bounded. This can go very large. If the smaller s is, this can become a very large function. Nu need not be a bounded function. And we'll say that nu is epsilon pseudorandom with respect to a test function f, if exactly the most natural thing happens, that is, if nu is epsilon indistinguishable from the uniform measure. And these are all from 1 with respect to phi. Okay. And I'm going to define sort of a new, so given, I'm going to define, so let phi be a class of test functions. I'm going to define what I'll call phi to the k to be another class of test functions. It's phi going from x to 0, 1, which is a property. There exists phi 1, phi 2, phi t less than or equal to k, such that phi is equal to phi 1, phi 2, phi t. It's basically the product, the pointwise product of t of at most k functions from phi. As a test function, just multiply it by this. Okay, that's what I call phi k. And okay, given this, I'm now in a good shape to state the dense model theorem. Recall the statement, the picture which we had. So there was this set x. Let's take 2 copies of x. And nu is some tiny measure over here. Nu is some tiny measure. So think of nu as a measure corresponding to, say, some very small set S. And within that small set S, we have a set F of constant density. So F such that expected value of F is delta. What would the dense model theorem say? And nu is indistinguishable from nu is indistinguishable from the whole space. Say according to some, with respect to some set of functions. Last time we had the same set of functions. We wanted to now give that there exists, that's our key thing, there exists an f prime. Basically what we wanted to do was there exists an f prime which is indistinguishable with f with respect to this test function. That's what we wanted. Okay. And the dense model theorem is, we can now state dense model theorem. This is, as I'm going to state it in from Reingold. Let's just call it RTTV version of this one. It's the following. So phi is any collection of bounded test functions nu is a measure that is 0 greater than equal to nu and expected nu is 1. And f is some sort of sub measure such that 0 less than or equal to f less than or equal to nu pointwise. Now I want to give a sort of a dense model of f, and we want it with some approximation. We say that for all epsilon in 0, 1, there exists an epsilon prime, and this epsilon prime will be at most 1 over exp in poly 1 over epsilon, and a k which is poly 1 over epsilon, such that if nu is epsilon prime pseudorandom, with respect to phi to the k, then there exists a dense model x going from just 0 to 1. It is a dense model of f. Notice f prime could be very, very large, but f is a dense model. F is a bounded function such that f prime is epsilon indistinguishable from f with respect to phi. So let's stare at this. So what we want is a dense model of f with respect to the test functions phi. Then we are going to have to construct a pseudorandom subset in which f sits in, which is epsilon prime indistinguishable with respect to a slightly larger class of test functions, phi to the k. Okay, this is a slightly more general form than what I had stated last time. There was no k last time, and I hadn't explicitly said the dependence of epsilon prime in terms of epsilon. And the remark to make from last time is, last lecture, we were working with phi, which were the cut functions, Actually, if you make phi to be not the cut functions, but the convex combination of cut functions, this won't change the convex hull of cut functions. It's not hard to see that phi is closed under multiplication. And hence, phi to the k was k itself last time. I'll not do this. This is simple calculation. It's just product of cuts is another product of, is a convex combination of cuts. So that's the theorem which we'll prove. So the dense model theorem.
So Prahladh, I need some help in understanding what's
yeah.
So there were two boxes that you drew, and now so some of these things lived in the right box and some of these things lived in the left box.
Yes.
Yeah. So
let's go back to the thing. So let's go back to the picture. Yeah. So the way. So let's keep the primes in our picture. So think of x as integers up to n, and this small set is the set of prime numbers in it. It's a tiny set. Semerides theorem worked for any constant density set over here. So we wanted to, and we had a particular set of test functions. What are the test functions? Test functions are those things which the Semerides proof or Roth's proof involved. So we want this f and this f prime. So if we can show that there's an f prime such that with respect to these test functions can't distinguish f and f prime, then any property of f prime will also be inherited by f. In particular, f prime, Semerides theorem was true that it has on the primes of arbitrary long, it has progressions of arbitrary long length, f will also inherit it. So what we wanted, so we had a particular class of test function.
Prahladh, when we say f and f prime are indistinguishable, we compare them with respect to a common, we take an expectation with respect to a common measure, right? It looks like here f, when we are looking at properties of f, that is somehow mediated by this nu, whereas when we talk about f prime, it is uniform measure on the left.
No, f prime is also mediated. Both the measure is always the uniform measure. Everywhere when I have put expectation, the measure is always the uniform measure.
No, but then f you will sort of scale with nu or something, because we want to know.
Okay. No. So the fact that f, so let's look at it. So forget about nu. Nu doesn't exist in the primes picture. There's only f, and we know any constant density sets in X. If we are able to show, so nu doesn't exist for us. There's just an f right now. Let's go back to the primes example. Nu doesn't exist. There's a small set which is the primes, and if we can show that is indistinguishable with respect to the test functions with some constant density set of all of n, then it will inherit the properties of that constant density. In particular, that constant density has primes of arbitrary long progression, so this f will also have.
So when you say it is indistinguishable, so
yes.
I mean, I would like to say that when you pick triples at random, what is the probability that they happen to be in arithmetic progression or something like that?
Yes.
Okay.
Yes.
So on the left hand side, I can understand that you're going to pick these triples by picking elements from X according to some rule. Okay. But on the right hand side, I presume that you would like to pick these triples by picking elements inside of this set nu or something like that, right? It's not still picking sets triples from the same distribution.
That is true.
So how should I think about it?
So it's what I said was false. The nu has to exist in the picture. Nu will exist in the picture. So
sorry, 1 second. But in some sense, f has already been scaled. So by saying that f is bounded by nu, that is nu majorizes f, we are sort of already saying that the f is not really the indicator function of the set that you're trying to find primes in, but it's already a scaled version of that.
Why?
I mean,
he's saying that f has already been
because it's already
boosted.
multiplied by n over mod s, right? I mean, if
it has been compensated for being from inside nu. It has been
It has already
compensated.
been compensated for being inside new. Yes.
Yeah. So basically, we want to say that if we look at the number of APs inside the set corresponding to small f and appropriately scale it up, then we should get the number of APs that are inside the set capital F, sorry, the set F prime. That's what we want to say. Without the
Yes.
scaling, it's impossible for the number of
Yeah,
APs
yeah,
in F
yeah.
to be
So,
equal to number of
yeah.
APs.
So, what I said in this one, I can't say it without that in the absence of new. There is a new there, and I agree. You are looking at the fractional number of Fs of. So here I'm looking at 3 APs, and I pick X, X, D, and I'm looking at. I'm picking a random X. So here, what do I say the number of 3 APs in a given set? It is pick a random X, pick a random D, and look at what probability X is in F prime, X plus D is in F prime, X plus 2D is also in F prime. This is what happens over here. Here, the same thing I'm going to play. I'm going to pick X, D, both from new and ask what's the probability that X is in F, X plus D is in F, and X plus 2D is in F over here.
So rather than saying X is in F for something, think of it the following way. The left-hand side, F prime is going to eventually be a function bounded by 0 to 1.
Yes.
So if we sort of think, I mean, like, let's cheat a little bit and say that it's actually a Boolean function. It only it takes values either 0 or 1. Then F prime corresponds to a set. So now if you look at expectation of F prime of X, F prime of X plus D, F prime of X plus 2D, now you are truly counting the number of APs inside on the left-hand side.
Yes.
But what is F going to be? If new corresponds
F is going
to a
to be
set,
new is going to correspond to think of new as corresponding to a set and F as corresponding to a subset of new.
That's right, which means F of for any point inside the set, F is going to take value size of n divided by mod s.
Yes.
It's already scaled up. So if you look at expectation of F of X plus D, F of X plus 2D, what you are going to compute is the number of 3 APs that are inside the set corresponding to F multiplied with n by mod s the whole cube.
Yes.
So the scaling is already introduced.
Yeah. So
because I mean, you need to compare apples with apples, so that's why it's there. I don't know if that answered Jayakumar's question.
No, got it. So the F I was thinking of was still the indicator function.
No, it's not the indicator function.
But it turns out that the F that you are thinking of is sort of F divided by new.
Yeah. So go to this. So new is this guy. So F will be there was a further set which I say call R within S, and F is not the indicator of R. F is new times indicator of R.
No, indicator of R divided by new.
No, new is already new already has this multiplication factor.
Yes. So
everything is going.
No, we want to cancel the new. So I think no.
But the expectation is still over. I mean, the expectation does not involve new at all.
That's right.
Yeah, the expectation is always over the uniform distribution. I don't know if that's the reason why you're thinking of canceling new off, because the expectation doesn't have new in the picture.
Okay. No, so you got it. I mean, I understand that you have compensated for being inside new by scaling F suitably. I mean, scaling the indicator function suitably. That's all. I don't know whether I'll get the numerator denominator right ever, but anyway.
So this is sort of S, that is R, and that is the ideal dense model which we called M or A last time. Okay. Now let's go back to the statement of the theorem. So new is some measure. So ideally think of it as an indicator of a small set, but scaled up to account for the size of the set being very small. And F is just basically a subset of new. Of this, there's a set new corresponds to a set yes. F corresponds to a smaller set of some density delta. I should mention one more thing over here, which I didn't do. This is 1 and 2. That expected value of f is equal to expected value of f prime, which is say delta. That is the fractional size of f prime in the unit thing compared to the fractional size of f in this one. Both of them are delta. So is the statement clear? You want to, Ram Prasad, Jayakumar, anybody, if you want to add to the statement, it will be good if you want to add more to it.
I don't know. It seems clear to me. But
okay, Jayakumar, are you okay now or?
Yeah. Fine. So, I mean, you said that this statement is in like this is a more general form. But it looks like it's actually the assumption is stronger, right? New is now required to be pseudo-random with respect to this product phi to the k.
Yeah. It's just so happened that last time the test functions we were considering, which were the cut functions, they were closed under multiplication. Phi to the k was phi itself.
Okay.
So because of that, for the specific case, for the specific application to the primes case, phi to the k happens to be phi itself. Therefore, it turns out to be simple. It's just that if I want this to be indistinguishable this way, what is the property? I would need a requirement on new, a stronger requirement. Firstly, it should be with a larger set of functions classes, and also it will be much closer to one than f is to f prime.
Got it.
Okay, it so happens in the this one. These are one of the simplifications which Conlon, Fox, and Zhao did in their paper. They observed that if you work with cut functions, then you don't have to do this, and that simplified things. Because previously it was not the cut. The original proof of Green and Tau followed Gower's proof, and therefore the norm that was being used was a Gower's norm. And so the test functions were the test functions coming from Gower's norm, and they were not closed under multiplication. So you'll have to work with a richer class of functions. And the original proof of Green and Tau had this. It was this observation, this simple observation. This observation is due to Conlon, Fox, and Zhao. They observed that you could work with a cut norm rather than the Gower's norm, and the proof will go through. And the Gower makes it simpler. It comes at cost. This part of the dense model theorem, this part becomes simpler. This one, the counting lemma becomes more complicated. It's elementary, but it becomes more complicated. It runs in the Gower's case. I think the counting lemma was just 1.5 pages long. In this case, the counting lemma is like 4 pages long. So it's an elementary proof, but 4 pages long. Yeah. Okay. So given this, let's go ahead and try to prove the statement. So proof. We'll start with the so let f delta be the set of all functions which are from. We want to show that given a, let's call it f prime. We are given an f. We want to show there's an f prime in f delta such that expected value of f prime is delta. So what do we need to show? So the DMT need to show there exists an f prime in f delta such that f and f prime are epsilon indistinguishable with respect to phi. Now, suppose not for contradiction. What we will try to show, the way the proof will go is, suppose this were not the case, we will show that there is a distinguisher. Suppose not for contradiction. That is, for all f prime in f, there exists a test function phi in phi such that which distinguishes these two. Considerably. Suppose this were the case. What I want to now actually show is this test. What we would like to show is this test, or rather pull out from this test function and show from this test function I can produce another test function, say phi prime, so that that phi prime distinguishes nu and 1. That's going to be our strategy. So phi is sort of distinguishing this one. Of course, there is no one single phi over here. There are multiple phis over here. So let's suppose, I'm going to make a simplifying assumption here. We will, that is, this is going to be a what we want to sort of a simplifying assumption. So suppose the following, let's say suppose this following magical property were true, then I want to say the proof can be done. Suppose the following were true. Suppose the following were true. There exists an f prime in F and a corresponding distinguishing phi such that f prime of x is equal to 1 for all x in support of phi. Suppose this were true. That is, there existed a particular f prime. Sorry, not in this one, and f delta. Then I want to show that I can actually use this phi itself to go and distinguish between this one. And that's not hard to see. Well, what do we have? We have that f minus f prime and phi is greater than or equal to epsilon. Let's drop the absolute value. Let's just assume this. We have this, that is f phi is greater than or equal to f prime phi plus epsilon. Now let's look at what is nu phi. Phi is non-negative. Therefore, this is certainly point-wise, it's greater than f phi. What's 1 phi? By our assumption, by our simplifying assumption, this is exactly equal to f prime phi. So I have only.
Can you
hello?
Can you hear me?
Yes.
Yes. Can you explain this equation once more? This nu dot phi is greater than or equal to f dot phi.
This is because nu majorizes phi. Sorry, nu majorizes f.
But then
and
phi
phi is non-negative.
Are we assuming phi is non-negative?
Phi is a test function which was non-negative. Yeah.
Or
the actual proof. The later on the proof I won't have. Right now, let's just keep phi to be non-negative.
Okay.
Phi being non-negative. Yeah, let's just keep phi to be non-negative. The actual proof, when I see it, will not require this. But in this case, I want to say, then if I can get this pair, such a pair, I can now produce this one. I'm done because I only made nu phi larger and one phi remains the same. Therefore, phi epsilon distinguishes nu and 1. Yeah, but the simplifying assumption is too good to be true. So we will have to work harder. So we will slightly work harder. So we want to get.
Prahladh, just like,
sure.
Is it one of those arguments that basically a small number of phis covers all possibilities, and you basically take the phi1 to phi k? That is, we are now trying to say that somebody claims that there is no f prime, right?
Yeah.
Yeah. So we want to say that
no, they want to say that for every f, for every f prime, there is a distinguishing phi.
That's right. So yeah, so no f prime is able to fool all the phis, right?
Yes.
Yeah. So and from that, we would like to say that somehow a small number of phis can be obtained, which will somehow cover the whole space, and that would lead to some contradiction between new and the all ones function.
Yeah, so but they don't come to that small number of ones right away in one shot. The way they want to say is, so let's look at this statement. Let's look at this statement. So for first, we are going to ask, let's look at this statement. This
Please
we
go
have,
ahead as you wish to do. I was just
no. So
trying to
yeah,
guess.
so but let's, so we're going to get this. We have this statement. I want to pull out sort of the best phi. This one, but there is no best phi distinguisher phi. For every f prime, there is a phi. But you can sort of use sort of the two-player zero-sum game to show that there is a convex combination of phi that distinguishes every phi prime, every f prime. I will state that in a second. So what we will do is, firstly, we'll do two things. So the question which this one, so we will firstly close the test functions. So we will do two things. We're going to, what I will do is I will do two proper things. Firstly, I will close it under negations. So I will work with not phi, but phi union. What do I call this? Minus phi. So this firstly, this will already see phi prime to be this object. We'll work with this test function, that is, so that we can always assume close under negations. Why does this help us? Once we are done with this, we know that for all f prime in f delta, there exists a phi in phi prime such that f minus f prime phi is greater than or equal. That I'm taking off the absolute sign because of this. This is only for the point of taking off the absolute sign. Since phi prime is closed under negations. I want to say, once we have such a statement, they must exist. Then the following claim should be sort of evident from this. That is, there exists a convex combination of a phi in the convex combination of phi primes, such that for all f prime in f delta, I'm changing the order of quantifiers. Basically, f minus f prime phi bar is greater than or equal to epsilon. Notice this is so. We will prove this, but this might be immediate for some of you. That is, this is all I'm giving you is for every f prime. I tell you there exists a phi such that this happens. Then I claim that there exists one nice phi prime, which is not possibly one of the elements in phi prime, but it's in a convex combination of phi prime, such that it distinguishes every f prime from f. Do people see this, or should I give a quick proof? Jayakumar, do you see this, or?
It looks like some LP duality, right? I mean,
it's an LP duality. I'm just going to set up a zero. So I'm going to just set up a two-player zero-sum game. It's LP duality or min-max theorem or one of these things, zero-sum game, in which both players, this player one, player two, both of them have common knowledge of f is given to them. Player one is picking up f prime. Player two is picking up f prime and f delta. This is what this guy is picking up. This guy is picking up a phi in phi prime. And the payoff to player 1 to player P1 is exactly F minus F prime phi. And it's a zero-sum game, so playoff to player 2 is minus F prime phi. So it's a zero-sum game. So in particular, since it's a zero-sum game, because it's a zero-sum game, there exists an alpha, which is the value of the zero-sum game, and two mixed strategies, which particular F prime bar and phi bar, such that the following is true. What is it? One, A is the fact that for all the phi, for all F prime and F delta, F minus F prime, phi bar actually gives you greater than alpha. And B, for all phi in phi prime, F minus F bar phi is less than or equal to alpha. That's the property of a zero-sum game. That is, there's a mixed strategy for this guy in which he can guarantee okay. But then we are almost done, because for instance, we do know F bar is also an F delta. A convex combination of things which are delta is certainly this. So in particular, we know that there exists a phi corresponding to this F bar, such that F minus F bar phi F bar is greater than or equal to epsilon. But on the other hand, for all phi, we know this. Therefore, hence alpha is greater than or equal to epsilon, and then you just plug it in. Then alpha is greater than epsilon. Hence, the claim follows from. Yeah, this right now, it might seem a little elaborate, but this is just LP duality going on here. So just LP duality. I'm just saying, if I have this condition, basically all I'm saying, if I have this condition, I can change the order of quantifiers. I can get this over here, but that comes at the cost of, I won't be able to get a phi in phi prime. I'll get a phi in only in the convex combination of phi prime. LP duality guarantees this, and that's all. LP duality is what is taking you from here to here. It's changing the order of quantifiers, but it comes at a cost. You cannot no longer have a pure strategy. It will be a mixed strategy. Okay, so this is going to be our phi prime. This phi bar is what we'll work with, and we'll sort of show that from this phi bar I can extract a distinguisher. This phi bar is distinguishing F from every set in F bar in F delta. We will use this phi bar to actually get a distinguisher for between nu and 1. Okay. And to get this and the thing is sort of going to be motivated by this sort of proof strategy, this one. What we want is this phi bar to be actually, we would both want F bar and phi to be sort of, firstly F bar to be a 0-1 function. So what we will do is the following. Let's do this. So let's look at phi bar, which is a function from x to now minus 1, 1. It's some convex combination of the test functions. So think of it, this is x, and I have lined up x in the decreasing, this is the sort of histogram for phi. That is, and I lined it up such that the larger phi is largest on the leftmost and small decreases as you go to the right. These are elements in x, and this is phi of x. This is particular x, and this is phi of x. Okay, so this is between here it's between here this is between 0, -1, 1. Okay. Now let's pick up the, what I'm going to do is I'm going to pick up the let S be the delta mod X elements of X where phi is the largest, phi is maximum. Basically, I'm going to pick up this band. I'm going to pick up a band of size delta mod X among the largest case. We should not be using S for this. Forget the S pictures which I had talked about in the past. This is the S. And notice that, and also let's assume delta mod X is an integer. It's not, there's no this one. So let's look at the function f prime equal to indicator function of S. So what is f prime? F prime with, what's the expected value of f prime? Is delta, way I defined it. Therefore, in particular, that is f prime is also a member of this f delta. So in particular, phi, the phi bar distinguishes epsilon distinguishes f from this f prime. Let's call it 1s. F prime is a generic thing. So in particular, we have f and phi bar is greater than or equal to one s phi bar plus epsilon. Okay. Now, what do I want to do? I want to actually, what's the best way to describe this? What I want to do is, phi bar is an arbitrary function between valued between -1 and 1. What we'll want to replace it is, I want to go to phi bar being a Boolean function. So I would like to replace in the above, replace phi bar by a Boolean function. No, suppose phi bar were a Boolean function. Suppose phi bar were in fact, suppose phi bar was in fact a function from x to just 0, 1. Then I claim we are done. Then we are done because why? Once again, the same thing will happen. New phi bar will be greater than or equal to f phi bar. The same argument as before, and 1s phi bar is equal to 1 phi bar. Or in fact, 1s phi bar can only be smaller than 1s phi bar. No. Am I right about this? Not right about this. Argument that's going to come later. Let me take back this. What I want to do is, you'll see, it'll be convenient if phi bar were actually a Boolean function. So what we will try to replace is, we'll replace phi bar by, we want to replace phi bar by, we would like to get a Boolean distinguisher. Not my argument that it's a Boolean distinguisher is a good value is not there, but let's see. We would like to get a Boolean distinguisher. And what's the function I'm going to construct? I'm just going to construct phi bar. Let t be any number between -1 and 1. And phi t is just going to be the indicator function that, so just define this phi t bar from, just define it this way. It's the indicator function that phi of x is greater than or equal to t. So it's a step function. If phi of x is larger than t, output 1, otherwise your output 0. Note, it's easy to see that if you integrate -1 to 1 phi t of x dt, what is this object? This is just -1 to phi of x. Let's write it down. -1 to phi of x, indicator of phi of x greater than or equal to t dt, plus phi of x to 1, the same quantity. Notice this guy is always satisfied. This is always 1, therefore this is just phi x plus 1, and this is always 0. So for this integration is just this quantity. Therefore, what do we have from here? So I'm just going to replace the fact that we had f of phi is greater than or equal to 1s, sorry, phi bar. Everything is phi bar over here. Epsilon. I can just replace this by f integral phi bar t dt minus 1 . Okay.
No, I got confused. So integral is a number, right? So maybe you meant something else.
Integral is a number. So integral is a number. So it's a integral. This is for per x value. So instead of phi bar, I'm putting this function.
Okay. You're right. This is a function. This is a function.
It's a function of x now.
Yeah.
It's still a function. So
Yeah.
a function of x, I'm just replacing it.
Got it.
Okay. And note that f of 1 equals delta. This is exactly expectation of f. And 1s of 1 is also delta. Therefore, I can drop off this one. Therefore, we have this quantity f. So let's get the integral outside. Phi t dt is greater than or equal to integral 1s phi t dt plus epsilon. And the integral is going from -1 to 1 in both cases. This will sort of tell you that there has to exist a threshold function for which this is true. The integral of it's sort of the expectation of this inequality is true. There has to be exist a threshold function which is true, but we'll actually prove a slightly stronger thing. That is, it's not the same. The threshold function on the right hand side, it's true. So this implies, this certainly implies there exists a t in -1 to 1 such that f phi t is greater than or equal to 1s phi t plus epsilon. This has to be true. But we'll actually prove a stronger thing. We'll prove a stronger statement. We'll prove a slightly more, not stronger, we'll prove a more robust statement. What's the statement we'll prove? We'll prove the following claim. There exists a t not in -1 to 1, I mean -1 plus epsilon by 3 and 1 such that f, these are all, once again, these are all phi t bars. F phi t bar is greater than or equal to 1s, not just phi t bar, but even with a smaller this one, but it comes at a cost. comes the threshold, the distinguishing factor from epsilon, it drops to epsilon by 3. And why is this true? This is just the proof of this is fairly simple, given what we have. So suppose not, then let's just look at the integral we have, -1 to 1 in integral f pt dt. So we know that for every t, this is false. Therefore, it's good to split this as -1 to 1 plus -1 plus epsilon by 3 f pt dt plus the region where it is false. dt. Let's bound both of them. The first one, -1 to -1 plus epsilon by 3. F is positive. Pt is a number between -1 and 1. So I can just replace it with f1 dt. Here, I'm going to upper bound it with 1s all bars pt minus epsilon by 3 plus epsilon by 3 dt. That's a strict inequality because I have assumed for contradiction. But what is this? F1 is delta, that's a constant, and it's ranging over a small epsilon by 3. So this is just delta times epsilon by 3. This one, this is a 0,1 function. This is also a 0,1 function. It's ranging between the regions -1 plus epsilon by 3 to 1, this one. So I'm just going to extend it all the way. -1 plus epsilon by 3 to 1 plus epsilon by 3, 1s p bar t minus epsilon by 3 dt. Just upper, I'm upper bounding this. And this is a region 2 minus epsilon by 3 into epsilon by 3. Delta is some number less than 1. Therefore, these two together sum to at most epsilon. Delta epsilon by 3 plus 2 epsilon by 3 is at most epsilon. And this is this one. So therefore, this is at most plus epsilon. But this is a number which is at most 1. This is a number which is exactly 1s, integral 1s phi t bar dt. There's just a change of variables is going to get me this. But this contradicts the statement which we had here. Sorry, not the statement, not the statement, which is the statement which I wanted. This statement. This contradicts. In particular, that's the end of proof. So we have the following. We have a distinguishing function. We have f pt bar is greater than or equal to 1s pt bar t minus epsilon by 3 plus epsilon by 3. I claim now we are already in pretty good shape. So there's one more observation I want to make, and once then we have made a question. We want to, the point to notice is new ft bar is only larger than this. New ft bar is larger than this, and I want to get that one ft bar will go smaller than this. So they will get distinguished even more than what this is happening. This is what, right? Jai Kumar, if you can, you following or have I lost you?
No, I sort of get it. Please go ahead.
Yeah. So we have this. So the next one claim I want to make. So I would like to say this is more or less here. So there's a property which of this one which we haven't yet used. So what I want to make the now claim is the following: is the support of phi bar t minus epsilon by 3 is fully contained in S. Recall what was S? S was S and phi t. S is the topmost. Is the largest. Is the delta mod x elements of X which are the largest value of phi bar. Now I want to say that this is what S was. Now if want to claim, what do I want to claim? I want to claim if this is the statement I want to claim. If there's even one value in the support of phi bar t minus 3 which is not in S, that means there's some element in S. Let's look at this picture. Let's read the proof of this. Let's read all this picture here. What was S? We call S was we call S is the set of delta mod x largest valued elements of X according to phi bar. Now, if there's even one place in the support which is outside X, S, then I want to claim everything outside the support of this one. How do I want to say this? If there's even one thing out, because S is the largest guy, even if there's one value of one thing in the support of this one which is outside S, I want to claim everything outside in the complement of S, phi bar t minus epsilon by 3 should be Z. Is that what I'm going to say? I want to say, is that what I want to say? 1 second. Yeah, this is exactly what I want to say.
Can you remind me what is the property of this T in the claim above?
No, the T was just no. The T was just has this property. That is for later on. Notice that we wanted to get a Boolean function.
Yeah.
We wanted to get a Boolean function. So we had this. So the way to think about it is we had this particular statement with us. This distinguisher phi bar was not a Boolean function. For some of the things which I'm going to say next, it will be good to have it as a Boolean function.
Mm-hmm.
So because of that, we are replacing this phi bar as an integral of viewing phi bar as an expectation of some Boolean functions. This is just in the most natural way. The several threshold functions.
Mm-hmm.
Okay, and it should be evident that because we have this integral, there will be one T for which this is true. This is just the phi bar T is an integration of this. But this claim says that we not just, I just don't have this statement, I actually have it a slightly more robust statement at the cost of a smaller gap.
Yeah.
And we will need this for later on because phi bar T is not the class of distinguishers I get. I'm going to get a different class. I need to work with a different class of distinguishers, and for that's the reason why this is happening. We'll see that why that's happening later. So, and just this is slightly more robust. This statement is obvious because the phi bar p, the expectation of phi bar p is exactly phi. Therefore, and we had this statement. Therefore, this just is an evident statement from this. Here, this is a slightly more robust statement. That is, even if this side, even if I chose t bar to be a slightly smaller quantity, this is still, the gap is maintained, but with a smaller, this is what, that's what this claim did. So this claim, for now, think of the t bar as just some t like this. It's a slightly more robust version of this. So now you have some t of this form, but now I want to say that no matter which you take this, so phi bar t minus epsilon by 3 is 1 exactly. The support of this is exactly on all of those phi x, for which x is larger, phi of x is larger than t minus epsilon by 3. This is going to be 1, elsewhere it's going to be 0, this quantity. So let's look at this picture again. Yeah. So this is the largest, the delta mod x largest, guys. That's our S. And then there is a, and there's a particular threshold. There's a particular threshold which is t minus epsilon by 3. And let's use a different color for that. There's a particular threshold t minus epsilon by 3, and everything above, when above that is this one, and after that becomes 0. This is the function phi bar t minus epsilon by 3.
Maybe this horizontal bar should be a bit above because you want
the horizontal bar should go all the way up to 1. Yeah, so it will be like this. Okay. Now I want to claim, suppose this horizontal bar went beyond this. Then it must be the case. What must be the case? Then it must be the case that.
Can you draw the picture again? I mean, phi bar of t is all. So you are thresholding, right? So
I'm thresholding, yes. So this is this picture.
Yeah.
Delta mod x is the largest. Yes.
Yes, and
now
then you draw the horizontal line at t, or to compute phi bar of t, right?
Yeah, phi bar of t minus epsilon by 3, say. Okay, I want to draw this horizontal line. I want to ask, does this horizontal line,
and when you draw a horizontal line, what do you do with it? You look at all those places where the
so once if this is the horizontal line, if this is the horizontal line t minus epsilon by 3, the function phi of s will be 1 on all of these, and it's going to be 0 on these guys.
That's right.
I want to say this picture can't happen. It has to actually, t minus epsilon by 3 should be over here. So the t minus epsilon by 3 can be over here, or it could be higher up over here. So I want to find out which of these two cases it is.
So there is this point of intersection of the blue line and the blue vertical line.
Yes.
And your point is that the horizontal purple line has to meet to the left of that point of intersection.
Yes. Yes. If that does not happen, my claim is, say that, suppose that does not happen. That is.
So the bottom blue line is what you have.
Yeah. So suppose there exists an x. So both the bottom blue line, what is there? There exists an x not in S such that phi bar of x is greater than t minus epsilon by 3.
It's a point between your vertical blue line and a vertical purple line, right? Such an X.
Yes. Yeah. Then this, obviously this says that, the way the picture happens is, this will happen the other way. So S will be then contained in the support of the 1 minus phi bar t minus epsilon by 3. Sorry, S complement is going to be contained in, if this happens. Just by the way picture I have drawn over here.
S complement is things to the right of the blue line, blue vertical line.
Yes.
And you are saying that that is in the support.
Sorry. Sorry, I want to say the other way. I want to say this direction. This is contained in S complement, which is that's what the picture says. No, this picture is going to say that either S is contained, because of the way the thresholding happens, either S is so all I want to say is, let's state it. Let me state it in a nicer fashion. Recall S is this one. So only one of the following can happen. Either S should be one of the two should happen. Either S should be fully contained in the support of phi bar t minus epsilon by 3. That's the first line. Or S bar, or the complement of the support of phi bar t minus epsilon by 3 should be contained in the complement of S bar.
Complement of S.
Yeah. Only because the way thresholding is done, this is the only thing that can happen. Thresholding, and you're choosing the largest case. So either the line, either it's this line, or it's this line. Either it meets it above this point or below this point. And if it meets it over here, this is the case. If it meets it over here, this is the case.
Doesn't the first one imply the second one? It seems, I mean, maybe I'm saying something very stupid, but if you have A contained in B, isn't it true that complement of B is contained in complement of A?
What am I saying over here? So let's statement. So the first one, what am I stating? If it's contained this way, I want to say the support of this function. Sorry, this is not what I wanted to say. That is the whole reason. So this is in the first thing, it will be that the support of phi bar t minus epsilon by 3 is contained in S. That's what is happening over here, because this line is shorter than this. Or the support of the complement, this part is contained in S bar. Now they are not. So what I had written previously was false. This is what we have.
Yeah, and now it seems to make much more sense. Right. Yes.
Yeah, one of these two should be true. By definition. So by definition of S, not stated. Yes, either this or this should be true. What we want to prove, it's the former that is true. Suppose the latter is true. Suppose latter is true. Then let's look at 1s phi bar t minus epsilon by 3. I claim this is just 1s 1 because nothing has changed. By extending it to 1 everywhere else, I have not changed it. That is the complement of this is already 0 because of yes. So extending it to 1 all the place is not going to change the value at all. And this is equal to delta, which is also equal to f times 1 which is certainly greater than f times phi t. And this is a contradiction. This contradicts that f phi t is greater than or equal to 1s phi t minus epsilon by 3 plus an epsilon by 3. Okay, so hence I want to say this condition happens. That is, whenever, hence it's this case, support of phi t minus epsilon by 3 is contained in S. So this is the case, that this is this part is the, that's the picture that happens, and this is not the picture that happens. Okay. I'm not saying this very properly, but it's just thresholding, and the way, because I've chosen yes to be the largest case, this is the picture that's going to happen. Okay. Okay. So we are already done. So out at this point, why are we doing all this? At this point, going back to Abhishek's question, there's already a phi t. There's already a phi t that is sort of distinguishing a Boolean function that is distinguishing these two. And now, what do I want to state? So I have this function. How am I going to state this? So where are we now? What do we have now? What do we have? What do we have? What do we have? We have the following true. 1, there exists a t in -1 plus epsilon by 3, 1, such that f phi t bar, this threshold function, is greater than or equal to 1s. It's a slightly more robust thresholding, plus epsilon by 3. And 2, we have that support of is contained in 1s. Now I claim we have the result which we want to, more or less we have the result which we want to state, because this quantity, this nu comma phi t bar, is only greater than this. And this quantity, I want to say I can replace this with 1. I can replace this with 1 and phi bar t minus epsilon by 3. Because the support is contained, if I extend 1s by even larger, this is not going to change this inner product. So let's state that 1 and 2 imply that nu phi t bar is greater than or equal to f phi t bar is greater than or equal to, we have 1s phi t bar epsilon by 3 plus epsilon by 3. This comes from 1, and this is going to come from 2. This is equal to 1 phi t bar minus epsilon by 3 plus epsilon by 3. So we almost have sort of a distinguish. We have phi t bar or phi t bar.
Back to Abhishek's question. Phi t bar is a positive thing now?
Phi t bar is a threshold function. So it's 0 or 1. It's a Boolean function.
Oh, sorry. It's 0, 1. Okay, got it.
It's a 0, 1 valued function. 0, 1 valued function. That's the whole, this one. So because of that, this inequality is true. Because of that, it's a positive function. It's a non-negative function. This is the inequality which we have. And 2 is stating that you can, even if I replace 1s by 1, this is true, because everything in the support of this is contained in yes. Therefore, I extend it to even further higher up. It's not going to change the inner product. Yeah, but the point is, okay, so if I had, suppose I had done all this with phi bar of t, then I have got a threshold function that distinguishes these two. But the reason, so I needn't have done this with t minus epsilon by 3. I could have done it with just t for both of them, and I could have got this. The reason I'm doing it to be slightly better this one is because I don't want a threshold function of phi bars. I want to get a product of the phi bars rather than the threshold. If I had wanted to be the threshold, I needn't have done this claim at all. I needn't have done this claim. I could have just gone ahead and just started with this statement and finished the proof, and I would have got I've got a threshold of phi bars is going to have this property. There's a thresholding of phi bar that distinguishes nu and 1. My thing is running out of this one. Let me just get a charger and I'll put it charge. Just be on the line. If we wanted the distinguishing function between nu and 1 to be a threshold, we are already done. Threshold of our original set of test functions, then we are done. But what I wanted is not a threshold, but I wanted a slightly function. So here we're going to approximate the threshold by a polynomial. So we're going to use Westeros polynomial approximation. To state the following. So for all alpha beta in 0, 1, I want to claim there exists a polynomial. I'll say what this exists a polynomial P of Z. P of Z such of degree at most poly in 1 over alpha, 1 over beta, and coefficients of magnitude at most x spin poly 1 over alpha, one over beta, such that the following is true. What? 1. So let's look at how the polynomial behaves in the range between -1 and 1. I want to say P of Z is completely contained between -1 and 1 for all. It's completely contained between 0 and 1 for all z in -1 to 1. So the polynomial is bounded. The polynomial is sort of, if this is 0 and 1, the polynomial values lies between these two. And let's look at, I'm going to look at 2 points, t and t minus epsilon by 3. Let's call it t and t minus alpha. I want to say for all z in -1 to t minus alpha, the polynomial pz lies between 0 and 1 minus beta. Sorry, 0 and beta. So it lies, this is beta. So out here, the polynomial is like, so this is beta, and this is, I'm going to put 1 minus beta. I want to say the polynomial in the range between -1 to this one lies between 0 and beta. In the range over here, it's going to lie between, so it basically behaves like this threshold function. That is for all z in t to 1, p of z belongs to 1 minus beta to 1. So the polynomial behaves like this. So up from -1 to t minus alpha, it's always between 0 and beta. From t to beta, this picture is actually far wrong. So it jumps up. So the polynomial goes this way. So this is t minus alpha, this is t. So the polynomial is completely, let me redraw the picture. What are all the points here? This is -1, 1. This is 0. That's 1. That's the line beta. That's the line 1 minus beta. These are 4 lines. And then there's the line t minus alpha and t. Well, I want to claim the polynomial is fully between the 0 and 1. Between -1, 1, it's over here. Then it does something, it goes up. But over here, it's completely in this range. And you can get a polynomial in this type. Over here, by the way, over here, it could be going up and down several times. I don't care, but this is what I want to see. Polynomial Westeros, this one will give you such a polynomial. This is basically, I want to approximate the threshold function by a polynomial. And once I approximate a polynomial, I'll have product of test functions and I'll be done. So we'll just apply the above polynomial approximation with alpha equal to epsilon by 3 and beta equal to, say, epsilon by 12. So this will give us the following, that is p of z is always less than or equal to indicator of z greater than or equal to t minus epsilon by 3 plus epsilon by 12. This just follows from the behavior of the polynomial. I z greater than or equal to t minus epsilon by 12. For all z in -1 to 1. So hence we have the fact that phi bar t of x minus epsilon by 12 is less than or equal to p of psi of phi of x. Phi bar of x is less than or equal to phi bar of t minus epsilon by 3 of x plus epsilon by 12 for all x in x. And now I claim we are done. So now let's look at, so the distinguishing function will be p of phi bar. Let's look at it. It's new p of phi bar. By definition, this is greater than or equal to, f of p of phi bar. which is greater than or equal to f of phi t minus epsilon by 12. I'm using the first property. This is f of phi bar t minus epsilon by 12. This property, this is greater than 1s phi bar t minus epsilon by 3 plus epsilon by 3 minus epsilon by 12. This we already saw. This is exactly 1 phi bar t minus epsilon by 3 plus epsilon by 3 minus epsilon by 12. This once again by the polynomial approximation thing, this is 1 p of phi bar plus epsilon by 3 minus epsilon by 12. There's an extra other epsilon by 12 you'll get. So this is just 1 p of phi bar plus epsilon by 6. So what we get that p of phi bar, this polynomial of phi bar, epsilon by 6 distinguishes nu and 1. Therefore, hence, there is some phi bar of k, hence phi bar of I. Hence, there is some, so what's called it, k in 0, 1 to the degree this one, so that phi bar of k epsilon by 6 d plus 1 and the size of the coefficient distinguishes, because this is just a sum of all of these guys. So one of them has to distinguish, and that's the end of it. This is the epsilon prime, which we set to be. Yeah. Yeah, so it's in some sense this proof is, I'll quickly say what's happening in the proof and then stop for the lecture. So what did we have? So we had this, for every f bar we were able to show assume the contradicting thing were not true. Assume f and f bar were indistinguishable, where epsilon, we need to show they were epsilon indistinguishable. Suppose not, that is, for every f bar, there exists a phi such that this happens. We first closed it by complement. We closed it under complement so that we always have it, for every f bar, we always have a phi such that this happens. LP duality told us that there exists a single phi bar in the convex combination of the test functions, the convex solve of the test function, which distinguishes every f bar from f, every f bar in f delta from this. Now, we wanted to extract out a distinguishing from this. We wanted to extract nu and 1 to distinguish nu and 1. So phi bar was not a Boolean function. So we sort of we came up with a thresholding function to get a Boolean function. So the whole process of this, we wanted to get a sort of a thresholding function. So this, and it's easy to come up with such a thresholding function. Where is this? This thresholding function, but because eventually, but we wanted a slightly more robust version, so we got a thresholding function which works slightly more robustly. Here it's phi or t, and here it's t minus epsilon by 3. I came up with the loss. Once we have this, we just approximated the threshold function by polynomial Westeros equation, and we got the completed the result. This is calculations wise. There's a lot of things, but basically this is the entire proof structure going on over here. So RTTV have a very nice exposition of this. I will put that up on the web page. I will add the reference to it, and you can see it from there. Yeah. Questions? So if you look up the original paper of RTTV, they actually show how this generalization of the dense model theorem, which was proved for the Green Tower result, is actually proves several other it implies the hardcore set lemma, various other things in TCS also have this is the underlying result behind it. This is sort of a general abstraction of several of these statements. Yeah, and I'll keep that aside. You can look up that paper. It's a very well written paper and you can look it up. I think I lost a fair number of you guys. Ask me questions if you have any. Otherwise, will stop the class.
So, I mean, just a general question. I mean, see, you had this phi bar, and from that you needed to transit to phi to the k, that capital phi to the k. And this time you did it via this polynomial approximation and some surgery on phi bar, thresholding, etc. In many situations, you think of phi bar as a convex combination of things, and then you just sample and
so this was also
so that doesn't work here, or what?
No. So that also works. So there you can give the dense model theorem instead of doing polynomial Westeros approximation, you can replace it by you can put a thresholding over majority of a small number of functions. So if you actually look at RTTV paper, they say the distinguishing function could either come from the product set or from this set. You could use any one of them. For the CS applications, this majority sort of thing is the more useful one. It so happens for the primes, the Green Tower result, the product is the one is the more useful. The question is, if phi is the distinguishing set for f and f prime, what is the distinguishing set for nu and 1? So you could have either what we have done. I gave up the distinguishing set there was this richer class, which was the k-wise product of utmost k-wise product of utmost k functions from the smaller class. You could take it to be other thing is take a majority of k guys, and that's also this exact same proof will give you the same thing. Instead of doing polynomial Weierstrass, you do sampling and Chernoff bound.
Yeah, that's what I was expecting in the beginning.
So that's what. So that's so RTTV is written in both these. They have both these conclusions from it. For the primes in AP, you need this multiplicative property, and therefore they Okay, I'll stop with this. We might have one or two more lectures in which I will introduce we'll change gears completely, introduce a topic called high dimensional expanders and talk about this object. It's been in the news recently in the theory TCS community. We'll talk what this object is. And if time permits, we might also see an explicit construction of one such high dimensional expanders. This will be next week. Tuesday, and if it overflows, Tuesday and Thursday. I'll stop with this. Okay.